Okay, so good morning, everyone, and welcome to today's TSU's present online seminar. I'm Ren Kai-Xu from TSU. So it's my pleasure to introduce our speaker today, Dr. Nick Pedatella from the High Altitude Observatory at the NSF National Center of Atmospheric Research. So just a quick introduction to Dr. Pedatella. He is an expert in atmospheric science and got his PhD from the University of Colorado and back in 2011. And after that, he worked as a postdoc at NCA's High Altitude Observatory, and then moved to the UCA Cosmic Program Office as a project scientist. So before return to HAO in 2016, so his research mainly looks at how waves in the low atmosphere affect the upper atmosphere. And he used a mix of the satellite data and the computer model to study this. So he also really focused on using data assimilation techniques to make atmospheric model more accurate, especially for the ionosphere. So today, Dr. Pedatella will be talking about improved specification and the forecasting of the ionosphere-thermosphere through the data assimilation. So he will explain how this method, which is already common in the lower atmosphere, is being used to be better understanding and forecast the condition in the ionosphere and the thermosphere. So he will also share how this technique help us to improve atmospheric model and get it better prediction for the space weather, which is important both for the research and the operation purpose. So we are excited to hear what the Dr. Pedatella has to share us today. So without further delay, let's welcome Dr. Pedatella. Dr. Pedatella, please.
Okay. So first, thank you for invitation as well as kind introduction. I'm happy to be here and present this work today. And so this is work, as was mentioned, that's really focused on sort of improving the Earth's upper atmosphere through using data assimilation. And I'll explain in more detail the sort of methodology and then present some of the results. And what I'll present here is really collaboration with a number of people here at both NCAR, University of Colorado, and then we have long-term collaborators with Charles Lin and Koichi Chen there in Taiwan, who have been also working a lot on the data assimilation, and I've always enjoyed my visits there to Taiwan to work with them. So just briefly, what I'll discuss in this presentation is kind of first give some background on why we want to do data assimilation for the ionosphere and thermosphere, and then really I'll go into some of the challenges that are faced once you try to sort of extend the domain that you're trying to do data assimilation, and how it's a bit different than what would normally be done for kind of standard tropospheric numerical weather prediction. Then I'll discuss the data assimilation that we've developed for the two models developed here at NCAR that are whole atmosphere models. And then I'll discuss some of the impact of assimilating ionospheric observations on sort of getting better specification and forecast of the space environment. So first, I think this may be obvious to many people, but it's worth reiterating. Really, the purpose here is we want to improve our ability to specify and predict the conditions in the middle and upper atmosphere. Just like you want to, predict what the day-to-day weather is here, in the troposphere, we also want to be able to do that with space weather. And really, this is becoming more important as we're kind of, as a society, relying more on both communications technology that sort of traverses through the upper atmosphere. So that is one reason. And then, of course, there's kind of larger growth in sort of satellite constellations, and with that comes better need to kind of specify the neutral environment and how that impacts satellite drag. And here on the right are just some kind of headlines showing the sort of potential impacts. This was from I think 2022 when SpaceX, they lost 40 satellites due to a geomagnetic storm, and this is tens of millions of US dollars lost due to this sort of effects there. And then in more recent storm that happened in May, there was issue with sort of GPS systems not working, and this has sort of ultimate economic effects. So trying to understand this better is really crucial from a societal standpoint, and really what hopefully I can convince you during this presentation is data assimilation is kind of what I would see as a way forward that we would want to do this, because it really helps improve our sort of nowcast or specification, as well as the ability to forecast the middle and upper atmosphere. So why data assimilation? There's essentially two reasons, right? One, we can build very sophisticated numerical models of the sort of atmosphere, space environment, anything. But no matter what, when you build a numerical model, it's always going to be sort of missing some physics, have some issues because you cannot resolve all scales that are relevant. And this leads to some uncertainty, and then it will also be probably biased as well. It can give you, a rich amount of information globally, but really it's not going to give you, it's always going to have some errors. It will never be perfect. And of course, the contrast to just building models is to build instruments and observe things. But observations are always going to be limited in terms of what they can observe, where and when you can observe it. You're never going to be able to observe everything that you would want to. And there's one of that is just, limitation on where and when you can observe by the number of sensors, but also for a number of things, fundamentally, it's just a quite difficult quantity to observe, because there may just not be, easy ways to observe it based on, observational limitations. So that also presents an issue. So really what we want to do with data assimilation is kind of merge these two together. So we have a kind of methodology of doing data assimilation, which I'm not going to go into the technical details as much in this talk, but we essentially have a data assimilation algorithm that brings together observations with a model prediction, which is sometimes you might see referred to as a background model or a forecast. And so then we bring together the observation as well as this sort of background prediction, and then we get a corrected model state, which is often called the analysis. And then this cycle sort of repeats itself. So you would take this new model state and then kind of create a short-term forecast that would lead into a new sort of prediction, and then you would combine that with the next set of observations, and so on and so forth. And that way you're basically always kind of adding some correction to your model, and then your model can kind of fill in where you might not have sort of as rich observational information. You can leverage what the model would tell you. And this is the technique that is used by most sort of I would say, well, actually all sort of weather prediction systems for predicting tropospheric weather. Of course, now machine learning is starting to be developed and used there as well. But historically, this has been proven as kind of the only way to get reliable and accurate weather predictions for tropospheric weather. So for these reasons, we kind of implemented a data assimilation capability within the NCAR whole atmosphere model. And the reason we want to do this in a whole atmospheric model is really that the fact that the upper atmosphere it is driven both by kind of external forcing from the sun, so sort of large geomagnetic storms, and then just sort of day-to-day solar variability. But then there's a lot of kind of day-to-day space weather that is driven by internal atmospheric processes, a lot of which come up from the lower atmosphere. And at NCAR, because of this, we have developed this sort of whole atmosphere models, WACOM, which goes up to about 150 kilometers, and then WACOM-X, which extend up to about 500, going all the way from the surface. And these are part of the NCAR's community Earth system model. And really, the motivation for this is getting the sort of full set of coupling from the sort of Earth surface all the way up into the space environment. And these are widely used community models for studying atmospheric chemistry and aerosols, and in atmosphere coupling processes, space weather, and a number of other things. But typically they're run as sort of in a more what you could think of as a climate model type of mode, where they're not constrained directly by observations through data assimilation. So about a little over a decade ago, we started down this path of implementing data assimilation and in both WACOM, which, as I say, extend up to 150, and then WACOM-X, which is a sort of thermosphere, ionosphere extension of that. And really, as I said, this is to get better direct observational constraint of these sort of middle and upper atmosphere. And to do this, we made use of a software package that is developed here at NSF NCAR, which is called a DART, or Data Assimilation Research Testbed. And this provides a sort of framework for doing ensemble data assimilation. This kind of does the data assimilation part agnostic of the background model. So DART itself can be implemented with many different types of models, and it's been used for a number of different applications. But here we use that to kind of provide the ensemble-based data assimilation approach that we then couple with these whole atmosphere models. And there's a number of unique challenges to doing this sort of data assimilation that extends really from the entire Earth's atmosphere extending into space, and that's what I'll discuss next. But the reason for doing this, there's a number of applications. I'm only going to show kind of a few here, but by developing this capability, some of the things we can do with it are listed here. First, it can provide initial conditions for looking at kind of predictability effects. So by bringing in observations, we get a better sort of initial state, and then we can look at how that impacts sort of predictability or forecast skill. And you can then, being a whole atmosphere model, you can look at how lower atmospheric forcing kind of gives you better prediction of the whole atmosphere. So if you can predict, say, events in the lower atmosphere much better and how they propagate up, that might give you better forecast skill of some aspects of variability in the space environment. You can use data assimilation to estimate uncertain model parameters, right? Every model has some parameterization or things that are not really known perfectly. And there's possibility of using data assimilation to kind of estimate those parameters. Another thing that's I list here, this hasn't really been explored too much, but if you can generate a well-represented, essentially reanalysis by using the observation and the background model, this could potentially be used for kind of high-quality training set for developing machine learning models that generally rely on having this sort of high-quality reanalysis, which exists for kind of troposphere, stratosphere, but doesn't exist throughout the whole atmosphere domain. So as we're building this sort of system to do whole atmosphere data assimilation, there's really a number of, I would say, difficulties or challenges that make it much different and complex compared to what is done for conventional sort of numerical weather prediction in the troposphere. And this means that you can't just take what was done in a sort of standard numerical weather prediction, apply it to a whole atmosphere model, and expect essentially, good results, I would say. So the issues are here, and I'll go into each of these in a bit more detail. First, the sort of upper atmosphere, the way the system evolves in time is kind of driven both by internal dynamics and then as well as kind of external forcing. So this impacts a little bit how you have to do the data assimilation. Another aspect is the timescales of variability are very different between the troposphere and, say, the thermosphere or ionosphere. So this means is sort of how you do data assimilation also has to be a bit different. Another aspect is, smaller scale waves and things like atmosphere gravity waves. These kind of drive a lot of important variability. So the wave-driven variation is quite important to consider. Another aspect here is, compared to numerical weather prediction, we have a much more limited observing system in the upper atmosphere compared to the lower atmosphere. So this, you kind of need to do things to leverage as best as possible the observations that we do have. And the last point here, I'm not going to go into too much, but essentially, the models we have here are a bit more computationally expensive because we're spanning a, much larger domain. And so that means kind of running experiments and tuning things becomes a bit more of a computationally cumbersome process. So going into some of these in more detail and how they impact the data assimilation. So the first thing is this issue of the fact that the future state is partly driven by initial condition and also external forcing. So there's two ways you can think of as a sort of dynamical system. So if we start at a given sort of state and then we want to propagate that state forward in time, there's two ways you can think of this: as a sort of chaotic system, which is where if we have two, say, initial states here that are slightly different, and then we run this sort of system forward in time, the two states are going to diverge because the system's chaotic. So it's very sensitive to the initial condition. So as soon as you sort of change things a little bit, then it sort of spreads out. And this is the type of system you have in the sort of troposphere. This is the sort of, you may have heard the classic, butterfly flaps its wings and then that causes, a hurricane or typhoon. And that's this sort of chaotic type system. The opposite type of system would be a strongly forced system, where you have two initial conditions here that are, quite different, but because the system is forced, it's kind of independent of the initial conditions. At a later time, it'll converge to the same state because it's being driven by something else. And initial condition dominated systems are sort of like numerical weather prediction. Seasonal prediction of the troposphere is a little bit more dependent on some other kind of boundary conditions. Ionosphere-Thermosphere is kind of in the middle here. And you can think of things like, climate prediction is a bit more of a forcing dominated state where it's kind of dependent to a large extent on, the evolution of greenhouse gases. But the ionosphere-thermosphere is maybe here in the middle, where it does have some sensitivity to initial conditions, but the forcing is also an important part. And what this means is when we're trying to generate a sort of spread in our ensemble, which these sort of ensemble data assimilation methods require you have a sort of sufficient sort of spread in your ensemble for them to work correctly. This means that we kind of have to take into account the external forcing and how it represents variability. So these are some examples of electron density profiles. This is altitude, then electron density. And on the left here these are a number of ensembles in the black line, and the red is just the mean. This is if we have no sort of consideration of the external forcing in the ensemble. And you can see there is some spread, but it's rather quite small, especially in the upper parts of ionosphere as well as lower down. And here in the second from the left panel, this is when we include these sort of external forcing variability in the ensemble generation. And here you can see the spread is much larger in terms of, the variation relative to the mean, and it fixes some of these small spread here in the top of the ionosphere. And here on the right is just another sort of location showing something similar. So because of this sort of dependence on the forcing, we have to do different things to generate kind of spread in an ensemble data assimilation system for the upper atmosphere, because the system itself just doesn't generate enough spread from having sort of slight differences in the initial conditions. So we include these sort of forcing perturbations in some of the solar and geomagnetic forcing, as well as in the model, we have a sort of flux of O+ ions coming sort of in the top of the model, and we add some perturbation to that to get a slightly better spread here towards the top. So the other issue with sort of upper atmosphere data assimilation is that the timescales of variability are quite fast. So typically in a sort of numerical weather prediction in the lower atmosphere, data assimilation cycling, so this sort of where you bring in the data, do the adjustments, and then run a short-term forecast, would typically be done with a 6-hour data assimilation window. And the timescale of variability in the upper atmosphere is kind of much more rapid. So here on the left, this is a LiDAR temperature observations over the sort of in the lower thermosphere, mesosphere, lower thermosphere altitudes. And so this is from 80 to 100 kilometers. And then here on the x-axis is day. And you can see there's very, kind of rapid temperature variations on the order of, say, 50 Kelvin in just a handful of hours. So within one day, you see these sort of rapid variations increasing maybe as much as, say, 100 Kelvin within a handful of hours. And here on the right, this is latitude versus time. This is at one longitude of the total electron content in the ionosphere. And this is during a storm time period. And you can see here during the storm, there's very kind of rapid variations in the ionosphere. And if you were doing a 6-hour data assimilation window, say you assimilated data here at 24 UT, and then the next time step would be 30. And you can see there's all this variability within these two times. It would be a challenge because you're not sort of bringing in data at a regular cadence, and you have this sort of significant variation. So to address this, we've implemented a 1-hour data assimilation cycle as opposed to a 6-hour, and that gives us ability to capture these sort of rapid variations that you might see either during a geomagnetic storm or the sort of day-to-day variations you see at lower altitudes. So another issue is that smaller scale waves kind of play a significant role in the dynamics of the middle and upper atmosphere. Here on the right is just a picture showing this in the sort of real atmosphere observation. This is a convective storm event over United States state of Texas on the top here in the troposphere. And then here, hopefully you can see this okay on your screens. This is an air glow layer in the mesosphere. And you can see these sort of concentric rings, hopefully you can see them, that are basically signatures of small scale atmospheric gravity waves driven by this sort of convection. And these gravity waves have a significant sort of source of dynamical variability in the middle and upper atmosphere. So you need to sort of preserve these in your model because they're kind of an important source of true variability. But one of the issues is that when you do data assimilation, you're kind of making adjustments to, say, temperature or winds in the lower atmosphere, and these can sometimes generate sort of small scale waves that would look like gravity waves, but they're not necessarily real. And when these can get large amplitudes, and then they can have some consequences once they finally reach ionosphere and thermosphere. So to deal with this, we have to kind of do a lot of care in the data assimilation to make sure that we're kind of controlling the way the adjustments are implemented, but not excessively damping them too much, because if you add too much sort of damping in the model to eliminate small scale waves, then you sort of eliminate ones that are kind of needed within the model to generate the correct dynamics. So this is another issue, especially when you're developing a whole atmosphere model. You kind of need to address these as well. And then one of the last issues that we have to deal with is that your observing system is just not nearly as well developed. This is a plot from the data assimilation system developed by the US Navy. And on the right here, this would be similar for, I should say, any other model. On the right here is a look at this sort of observational coverage just from nadir sort of radiance observations. So there's other observations in the troposphere, stratosphere as well. But you can see at one sort of data assimilation time, you basically cover the entire Earth when you're looking in the sort of lower atmosphere. Whereas on the left, this is looking at the sort of lower thermosphere altitudes, where you see there is okay coverage, but there's still many sort of gaps or areas where you just have, very few observation, say here, also here. So in this way, we just don't have the number of observations that you see here. And what this means is that, you kind of really have to leverage the observations that you do have and make sure that they're really being used as effectively as possible. And when we move to even higher altitudes in ionosphere-thermosphere, there's very few thermosphere observations, but we have many ionospheric observation. But really, the ionosphere is kind of driven by the thermosphere. So this means we have to come up with ways where we can use the ionospheric observation to adjust the thermosphere, which then sort of really is what's driving the ionosphere. And I'll discuss that a little bit more later on. So how does all of these factors how does that dictate what we do for a whole atmosphere data assimilation system? First, as I mentioned, we have kind of shorter timescales, so we do a much more rapid data assimilation. We use 1 hour, but there have been people going to even less, say 15 minutes or 30 minutes. This external driving needs to be considered when generating model ensembles, because the sort of internal variability isn't kind of sufficient to generate a large enough spread for these sort of ensemble data assimilation methods to work. And then this issue of small scale waves and sort of how to prevent too much spurious generation from the data assimilation adjustments, and also kind of preserving the real waves that are existing. And then we need to make most effective use of these sort of available observation. And this last point, because of this sort of ionosphere-thermosphere coupling and wanting to use ionosphere data, we really need this covariance that gives you information about the thermosphere from the ionosphere really needs to be taken into account. So based on this, we've put together this whole atmosphere data assimilation system. They can assimilate data now truly from the surface all the way to the upper atmosphere. So lower down, this just shows here the observations assimilated. Standard sort of meteorological observation can be assimilated in the troposphere, stratosphere. Then there's some middle atmosphere temperature observations from NASA satellite mission. And then we can assimilate also data in the ionosphere from radio occultation electron density profiles, as well as ground-based total electron content, gold temperature observations, and then also wind observations from the NASA ICON satellite. And this is really the sort of first data assimilation system that can extend from the surface all the way to Ionosphere-Thermosphere. So first, I just show you a few kind of demonstrating results showing how it works before I get into a bit more of the detailed science. So here is showing in the troposphere, the 500 hectopascal geopotential height, just for 2 snapshots of 2 different days. Here on the top, this is latitude, longitude. The top is from the US NOAA Weather Service reanalysis product from NCEP. And then the bottom here is the data assimilation system we've developed in Wacom and Wacom-X. And you can see the general structure and sort of variability in the whole atmosphere data assimilation system in troposphere match quite well with what you would get in a modern reanalysis, including the sort of day-to-day variation. So you can see the difference between these 2 days, say this sort of growth of this enhancement here compared to here, we also see in our data assimilation system. And also these sort of features that's in the southern hemisphere, high latitudes, you see match quite well. So in the lower atmosphere, we're confident that we're reproducing the sort of realistic representation that you would see in a modern reanalysis. If we look into the mesosphere, so this is showing into mesosphere, lower thermosphere altitudes. The upper left here, these are temperature snapshot just at one time. This shows if we don't assimilate any observation. And the details here are not critical, but if you look at the sort of general level of temperature, you see it's in a sort of red to yellow type of color in general. And here are the observations that we're assimilating, sort of blue, green type of level of temperature here on the left. And you also see that from a different instrument here on the right. And when we assimilate these data, and have been cycling for a long time, we get something that looks like this. So these temperatures you can see are much lower. So we've sort of reduced this temperature bias that we have in the model by assimilating these data, and you get the temperature field that is in much better agreement with the observation. Here is just another example where this is a meteor radar wind. So looking at the wind around 88 kilometers. And this is just over a short time period. So this is 15 days. And you see there's a lot of variation here. And so the red is the radar observation. The black here is a different data assimilation model developed by the US Navy. And then the green here is our model from Wacom. And you see that the green line matches quite well with the other, with both the observation and the other data assimilation model. And so we're capturing these sort of day-to-day and shorter timescale variation seen in the observation as well as this other model. And here on the right is looking more at larger scale oscillations, where we have the model here on the top. This is a planetary wave oscillation, and this is over a full year, where you see there's sort of times where this planetary wave gets enhanced to larger amplitude, and then it's sort of decreased during other times. And here on the bottom is some satellite observation of the same sort of feature. And you see that the model can match the sort of temporal variation of the planetary wave variability quite well. So we're sort of capturing what you see in the observation here for the sort of planetary scale wave variability quite well in the data assimilation model. Here is one other case where we assimilate data. This is now altitude versus time. Here on the upper left is a model where we're not assimilating data above, say, 50 kilometers, which is this altitude. Here is if we assimilate the data, and here is the actual observation. The details here are not important, but I want to draw your attention to this feature here, which we call a sort of elevated stratopause that occurs after sudden stratospheric warmings. And if you look in this case where we don't assimilate this sort of higher altitude data, you can see it kind of descend very quickly, which is in disagreement with the observation where it sort of stays at a higher altitude. And so once we assimilate data, we capture that feature much better. And this dynamical feature has some implications for sort of chemical transport in the middle atmosphere. And here is the same sort of altitude versus time. Again, not assimilating the middle atmosphere data with assimilating middle atmosphere data. And here are observation. And you can see the sort of depth of this sort of transport of this chemical species sort of deeper into the atmosphere is much stronger when we assimilate the data than when we don't. And that's in better agreement with the observation here on the right. So we're getting sort of better representation of the dynamics. And here's one last kind of preliminary example. This is looking at the ionospheric perturbations. Top here is again where you don't assimilate the middle atmosphere data. Here is if we do, and then the bottom here is a proxy of the observation. This is local time versus day of year. And in the observation, you can see this sort of alternating pattern of kind of negative, positive, negative, and it sort of tend to propagate towards a later kind of local time as things go on. And if you compare with this sort of case where we're assimilating higher altitude data, it's in much better agreement than in the case where we don't. So we're getting much better representation of the ionospheric dynamics. So now I'm going to talk about a few case studies looking at assimilating sort of ionosphere data. So the first will be how assimilating ionosphere data can improve the thermosphere neutral density, which is important for satellite drag. So here what we do is we set up the so-called observing system simulation experiments, where we have a background run and we generate synthetic data. And then from that synthetic data, we assimilate it to see how well we can reproduce a known truth. So here we have a sort of biased ionosphere and thermosphere because we've sort of driven it with a different solar flux. So the sort of true case where we're generating these synthetic data from are on here, the bottom here with a larger solar flux. So you can see the density. This is thermosphere mass density at 400 kilometers. You can see it is much larger here compared to the case we're doing sort of if you had no data assimilation. So we're going to try to assimilate different data and see if we can recreate this sort of higher thermospheric density. And we do this with a few different experiments. One with kind of no ionospheric data. One where we assimilate the ionospheric data, but we just adjust the ionospheric state itself. And then the last one will be where we take advantage of sort of internal information in the model so that we adjust the thermosphere from these sort of ionospheric observations. So first, I just show you some confirmation that the ionosphere data assimilation is truly working. This just shows a snapshot. Here are the synthetic observations on the left. This is ground-based total electron content. Then these columns are different experiments. So first here is with no ionospheric data assimilation. This is the short-term forecast, then the analysis, and then the difference. Here you can see, if you look here, this is quite biased relative to the observation, which you might expect because we're not assimilating any data. And then in these other two columns where we assimilate the observation, you can see now the agreement between what we get in the both analysis field as well as the sort of forecast field is in much better agreement with what you see here in the observation, especially over, say, South America and the sort of African region, which are in daytime. For this UT, you can see much better agreement than if you don't assimilate any observation. And that's shown statistically here. This plot shows the root mean square error and then the bias. The different colored lines here are the experiments. And the black here is if you're assimilating just the ionosphere data. Red is if you also adjust the thermosphere. And the key point here is you can see the red is a little bit below the black. Of course, they're both much lower than the gray, which is the control. But really, this shows that when you sort of adjust the thermosphere state, you get a better ionosphere, and that the data assimilation is working as we'd expect. And now the key point is, looking at how can we adjust the thermosphere neutral density from these sort of abundant ionosphere data. So to do that, what we make use of is a sort of covariance information in the model. So we observe something like the ionosphere total electron content, but we can adjust the, say, temperature in the model if we know this sort of covariance. So this is obviously cartoon, but it's showing, say, for different ionospheric total electron content values, you have different values of temperature, and you can come up with a relationship between those two. And then when you adjust, say, the ionosphere value based on what you can observe, you can come up with a corresponding temperature variation, and then you can adjust that, and then you can get a better representation of these sort of unobserved states. So we leverage that by assimilating the ionosphere data to get a better representation of the thermosphere neutral density, which is what I will show you now. So these plots show the neutral mass density at 400 kilometers, just a snapshot at one time. So here on the upper left is this sort of truth case that we're trying to recreate. This is kind of what we know to be correct in these experiments. And then the right here is if we don't do any data assimilation system. And you can see there's a huge bias between the daytime and also nighttime thermosphere neutral density between this case and then the truth. And if we assimilate ionosphere data but only let it adjust ionospheric parameters in the model, we get something quite similar where it's very biased. Here on the bottom right is where we assimilate the ionosphere data and let it sort of influence the thermospheric state as well. And now you can see this bias has, it's not completely gone, but we've significantly reduced the bias in this thermosphere neutral mass density by assimilating these ionospheric observations. And here just shows the percentage errors. So in the case where there's no assimilation and impact on thermosphere, these two, you can see the errors are on the order of 40 or 50%. Whereas once we start to assimilate data, the errors are down to on the order of maybe 10 or 20%. So we can significantly reduce the error by assimilating these data. And here is just looking at this statistically so you can get a better sense of the reduction. Here on the top, these two curves are when you don't do this sort of adjustment of the thermosphere. This is, I should say, root mean square error. And then here in this sort of orange curve on the bottom is this assimilation of the ionosphere data and adjusting the thermosphere. And you can see there's a reduction in the root mean square error by on the order of about 50%. So we're essentially reducing the error by half in the thermospheric neutral density by assimilating ionosphere data. And it's interesting to look at how this might impact, say, a forecast. And this figure here shows what the forecast would be. So we stopped the model here, ran a forecast forward for several days. And you can see that, even though it's kind of a biased driving, just by adjusting the initial state to here, you get kind of forecast skill on the order of a day. So you can forecast this, it gives you some information, even if you don't have perfect sort of solar information. Just adjusting the initial state will give you this sort of forecast skill. So the other thing I'd like to briefly discuss is the impact of increasing observation numbers, specifically radio occultation data, and how that impacts this sort of specification and forecasting of the ionosphere and thermosphere. And so with this part, what we really wanted to look at is, if you really increase the number of observations, how would that impact what you get in the ionosphere and thermosphere? So not many studies have looked at this. There's a few. One result is shown here from a recent paper. The details of this figure are a little bit complicated, but it's basically a metric of how good the data assimilation is versus the number of observations you have per day. And this goes up to about 7,000. And you can see there's a general sort of decrease in the trend here of the, more observations give you better sort of skill. But these have been a little bit limited by only looking at, on the order of, in this case, 7,000. These are radio occultation profiles per day. So the question would be, if you go to a sort of much larger number, what will you get in terms of the impact? So to do that, we made use of this recent data set. It's called this ROMEX, or radio occultation modeling experiment. And this was motivated by the sort of meteorological community to look at how large numbers of radio occultation data would impact numerical weather prediction. So for this time period here in sort of 2022, September and October, they were able to collect large numbers of radio occultation data in the neutral atmosphere from a number of both sort of commercial companies, but then also sort of national or international satellite programs. And when you add all those together, you get something on the order of 25 to 30,000 profiles per day. Of course, most of these are sort of neutral atmosphere profiles in the troposphere, but here what we look at is what you would get if these were ionospheric occultations. So here what I will show is we basically did a similar set of these observing system simulation experiments set up as the previous experiments I showed you. And then we did 4 data assimilation experiments where we look at different constellations and how they would kind of impact the ultimate result. And here I'm just going to assume that all of the ionospheric profiles are occurring at the same time, location and time as the neutral atmosphere profiles. And then we add a sort of observation error that we know from the retrieval. And this gives us a sense of, if you had 30,000 observations per day instead of the current, say, 6, how much would that improve your sort of specification and forecast of ionosphere and thermosphere? So this shows the number of observations we have for the different experiments that I ran here. So experiment number 1 is on the bottom here. And so the solid line is the global number of observations per day. And the dashed is just if you look at low latitudes. So the black line here, this is if you just look at existing cosmic 2 observations. So you get somewhere on the order of 6,000 profiles, radio occultation profiles per day. The experiment 2 is in green here. And this is all of the ROMEX observation. So globally, you get up to about 25, 30,000 per day. And then I'll do a sort of middle ground, which is in the purple here, which is just 3 constellations, Cosmic 2, Spire, and this Yuanyao commercial system. And then I also run a control with no RO observations. So these are the 3 experiments. And now let's see the results. So these are profiles of the electron density, root mean square error relative to the known truth, and then the bias. So this is altitude versus error. And the gray here is, again, the control, so no observations. Black, just assimilating cosmic 2, and then the red, more observations, or sorry, purple more, green even more. And you can see there's a continuous decrease here in the number of observations, in the errors, both root mean square error as well as bias, as we sort of increase the number of observations we assimilate per day. So essentially, it doesn't saturate, it seems, going even from 20 to 30,000. So more observations, we're still getting an error reduction. Here's if we just look at low latitudes, same plot, root mean square error and bias. And again, you see this sort of continuous error reduction with increasing number of observations. And these are sort of analysis fields, but we can look at the short-term 1-hour forecast, and you get something similar where even the short-term forecast of ionospheric state is improved with increasing observation. So more observation is always giving us better information. And then if we look at this kind of statistically, how it varies with observations here in, so this is root mean square error. This is at low latitudes, 300 kilometers, root mean square error versus a number of daily radio occultation observations. Here is the analysis field in red, and then black shows the short-term forecast. And you can see there's not really a necessarily saturation here yet, even out to the number of profiles that we have available here. This is root mean square error. Here on the right is the bias. And again, you can see it, here a larger number would be better because it would be closer to 0. And you can see it's not really saturating. So even up to almost 20,000 occultations per day in the low latitude region, we're still seeing improvement. So that kind of shows that, a constellation just like Cosmic 2, which is down here, doesn't really give you, many more profiles per day, would give you, a much better specification and forecast. And then we did the same thing where we look at, how this impacts the thermosphere neutral density. This is similar to a plot I previously showed you, where we have the root mean square error versus time. And here is the control with no radio occultation data, just assimilating Cosmic 2 data, and then these other experiments. And you can see, again, more observations is better. So you go from a 22% reduction in the error in this case to a 34% reduction in the error by assimilating more data. So you're still getting a kind of significant positive impact, and more of these observations would be beneficial. So I've reached kind of the end here. So I'd just like to give a brief summary and some conclusion. I think that, well, first, hopefully I motivate you, for why we would want to do whole atmosphere data assimilation to get better sort of ionosphere-thermosphere state specification and forecasting. But there are some unique challenges that require sort of, unique ways to implement this. But I think we've done a reasonable job at that. And assimilating data in these whole atmosphere models really can improve representation of composition, dynamics, and even electrodynamics throughout the middle and upper atmosphere. And then, ionosphere observations, this can improve the sort of specification and forecasting of the thermosphere neutral density. And so I will conclude there, and I would be happy to take any questions that you might have.
Okay, thank you, Dr. Pedatella, for such an engaging talk. And now it's time for the QA session. So does anyone have any question? And please feel free to turn on your microphone and ask Dr. Pedatella. So any question? Okay, so I have one question. I'm not an expert in this field, but I'm interested in the challenge you mentioned regarding the atmosphere models, like a short time scale variability and the limits observation data. So could you explain a little bit more how and about how this challenge impact your current work with the Earth's atmosphere?
Yeah, let me go back to that slide and reshare my screen. So first, this sort of issue of, hold on a second, let me. Okay, I think you can see the slide, right?
Yes.
So the main issue, this sort of short timescale variability in kind of conventional ways of doing data assimilation in for numerical weather prediction, for especially global scale numerical weather prediction, you'd often use a 6-hour data assimilation cycle. So you're just bringing in kind of new information every 6 hours.
Oh.
And what that means is that, if you have very short timescale variation, you're not able to sort of bring in the observation quick enough to capture that. And so you would just be relying on the model itself to capture the dynamics of variability. So an example would be here, on the left, you can see these sort of very rapid temperature variability. So you could think if you had a very large, sort of time between you brought in these observations, then you're relying more on the model to sort of fill in the gaps, if that makes sense. So if we use we have to go to a shorter data assimilation cycle. And by doing that, then you kind of more rapidly bring in the data, and that, then you can adjust the model more frequently. So I think that addressed the other one. The question on limited data here is just kind of shown, how sparse the data can be. Here, it's kind of, there's only so much you can do. I mean, obviously, the first thing I would say is, well, we just need more data. Of course, that is always better. But the other thing I would say, if in cases like this, right, if you try to leverage the data that you have as best as possible, then you can get maybe more impact out of what you have, and that would give you maybe the best you can do with limited data. I think it's just important to keep in mind that, we don't have much observation, and so because of that, there's some potential consequences, right? Because you're sort of limited in the data itself.
Yes, it makes sense. So just a following question. So, and I'm just curious, if this model were to be applied to the other planets, such like the Mars or Venus, and would the main challenge will be also the lack of the observation data, and would the different atmosphere composition make the data assimilation even more complex?
That's a great question. So the first thing I would say is the background model that we're using, Wacom. I think some people are working on adapting that to work for Mars.
For Mars.
So it would basically be a Mars model that extended, from the Martian surface up to, the Martian thermosphere. And so there is a group working on that. In terms of doing data assimilation in Mars, I admit I haven't thought of that, too much. It would depend, I guess, how much data you have and
yes.
what you can do. I would think it's possible. I don't know if anyone has tried it. I'm not familiar enough. But these sort of tools are, can be applied to things like another planet or things like that. So it's not, impossible to do.
Well, that would be great. So, any question for Dr. Pedatella? So, I have one final question. So, with the advance in the AI and the machine learning, So how do you think this will impact the assimilation of ionosphere and the thermosphere data? So could AI provide more accurate or more efficient solution in data processing or the predict modeling?
That's another great question. I'm not sure I can give a perfect answer to that because we haven't really looked at it, and when I say we, I don't think anyone has. In the upper atmosphere, the sort of not many people are trying machine learning to the extent that it's being tried for kind of tropospheric weather prediction. And so I don't know how effective it would be because of, there are these limitations on availability of data, things like that, and how good you could really do. I think it's a completely open question right now. For some of these reasons, as I explained here, the system is different and things like that. That could mean that the way people are doing these sort of AI models for troposphere weather prediction, numerical weather prediction, are maybe not applicable to this sort of domain of the space environment. I don't know enough about how they train them and what potential consequences could be. But I think it's certainly an area I'm sure people are, if they're not already working on, they'll be working on in the near future. Because it's certainly been shown, I think, in the lower atmosphere that AI or machine learning models can do quite well. So I think we'll have to wait and see how it sort of turns out in the upper atmosphere.
Yeah, I think we were all really looking forward to such a development. Yeah. So if there are no more questions, I think it's about time. So let's once again thanks Dr. Pedatella for today's talk. Thank you, Dr. Pedatella. So please feel free to visit our TSU website to get the last update on the upcoming seminars. So thank you all for joining us today, and we will look forward to seeing you next time. And thank you, Dr. Pedatella. Thank you very much.
Thank you for having me.
Thank you. So good night. Have a nice day.
Have a good day. Bye.
Bye.